kind of got carried away there. 12:10.
Then let's go for it.
Let's go. He says, let's go. So Faye just told me I'm going to be giving the introduction. And this is one of those cases where if I gave a full introduction, Peter wouldn't have any time to speak. So I am actually going to just give a brief introduction. But for those of you who have not had the pleasure to meet Peter Tredici, this is a great way to get to know him. He is a senior research scientist emeritus at the Arnold Arboretum, who is now in year 40 with the Arnold.
40,
40
let's see, 1979, so.
Yeah, so 1979, he was in the Dana greenhouses, helping out with probably scrubbing pots and a variety of other things. And he's really been a member of our community ever since. And as I think all of you know, in some ways, Peter is every bit the heart and soul of the Arnold Arboretum. He's done a million things, from the horticulture to doing research. He got his PhD at Boston University with Richard Freemak, working on ginkgo. And he's been writing articles for Arnoldia forever. He's been traveling the world, giving talks, and well, I just think this is going to be great. So, as simple as I can put it, Peter, it's all yours.
All right. Well, thank you, Ned, for that. I really appreciate that. Let me turn this on. And hopefully you can hear me. Is that good for you? Okay, so this is a talk that I gave recently at the Worcester Horticultural Society. I got an award from them, and they said, well, in order to get the award, we want like you to give a talk about what you've been doing and stuff like that. So I developed it for that, but that was only about a half an hour, so I expanded this a little bit. So it's a real treat to be here and to talk about what I've been doing for those 50 years. That I started working for Harvard in 1972 at the Harvard Forest. So, over 50 years of working for Harvard University was something I used to be a little bit embarrassed about, but now I'm actually very proud of the fact that Harvard is a great place to have worked and to have been able to work for a long time. So what I'm going to talk about is resilience and rejuvenation. And this is what you see. This is a common mulberry after a storm blew down the tree. The ability of trees to resprout following traumatic disturbance. This has been a theme in my research over this whole entire period of that I've worked for Harvard. And you see it takes many forms. These are multi-stemmed red oaks following logging. And when you see trees in the woods like this is an indicator of their past use. And you see the same thing in Lawrence. These are some silver maples that were cut down by beavers. And so logging and beavers, you get the same response in terms of the trees. It doesn't make a big difference. And these are both species with incredible ability to resprout following disturbance. And in an urban context, the ailanthus is famous, the tree of heaven, for its ability to resprout following, in this case, maintenance, failed maintenance. But I'm going to talk more about the ailanthus a little bit later on. And some trees just begin to resprout as a function of senescent phase. They begin, this is a katsura tree at the Arboretum that has been here for how long? About 100, not quite 100, 120 years, right? Yeah, 1876. Okay, there you go. And the sprouting has happened spontaneously as the tree ages. It's too bad people can't do this, but and so the ecological implications, when you think about it, sprouting is a strategy that works for all sorts of environmental stresses, including fire, storm damage, browsing and grazing by animals, pruning by people, logging, flooding, drought, erosion, landslide, pests, and diseases. So it's not something that's adapted to one particular type of disturbance. It's a strategy that works for all sorts of disturbances, and that's why it's become so common. Seedlings resprout on virtually every tree seedling that I've ever seen has a ability, it's a universal trait, the ability to sprout back following an animal bites the top of it off, something happens. It enhances their survival both in disturbed habitats as well as closed canopy forests. But for a lot of tree species, the ability to resprout declines as they get older, but not for all. The ability of trees to produce secondary sprouts functions as an insurance policy. Again, so the trees invest in the ability to sprout in the same way that we invest in insurance as a protection against some catastrophe that could happen at some point in the future. This is my drawing. This is, when you can categorize sprouting in terms of the origin of those sprouts. If they come from the collar, that's where the root and the shoot system come together. You can have basic trunk sprouts from the stem tissue, or they can come from what's called a burl or a lignotuber, which is intermediate in terms of it's not really part of the stem or the root system. It's actually a very distinct specialized organ of rejuvenation that relatively few trees produce. Or they can actually come from rhizomes that originate from the trunk, and then those sprouts emerge some distance away from the original trunk. They can come from the root, and they can be root suckers. They're induced or by damage. They won't root sprout unless they're damaged, and then there are some that root sucker spontaneously. Or it can come from stem tissue itself, and which is when the stem touches the ground and takes root, it layers. So this is the basic taxonomy of sprouting that I developed quite a while ago. And now to start the actual lecture, I don't think I've ever shown this picture before. In the town of Harvard, Mass., where I lived when I worked at the Harvard Forest in Petersham, I bought a house there, and this was a picture that I inherited when I bought the house. The logging after the chestnut blight came in and killed all the chestnuts in the 1920s. This is the logging took place right next to the property that I ended up buying, and it was incredibly valuable wood because it's great for beams. That was the use. It's rot resistant and very, very strong. And this is it used to be when I first moved to New England in 1970, you could still see the remains of old chestnut trees as you walked in the woods. And this is the last one I've seen, 2003. The tree was, almost a meter in diameter. I mean, in diameter, which is amazing. But you don't see these anymore. At least I haven't seen them. Maybe in the Quabbin Reservoir you could find a few of them where it's not very disturbed. But what's amazing about it is that these chestnuts that you see in the woods that are sprouting, those were all either seedlings or saplings when the disease first arrived in New England in the 1920s. And those trees have been sprouting for 100 years. And the stems die, and then they send up new sprouts. So this is when I worked at the Harvard Forest, and this is in the 1970s. I used to be able to find a few chestnut trees. If they're growing on the edge of a woods and they get good sunlight and good water, they will produce fruit. And I collected quite a few seed, and I created a little plantation at the Harvard Forest when I worked there. I think it was in 1975. And then I went back there 25 years later, and I talked to the director, David Forrest. I said, I'd like to dig up some of those and see what's actually happening 25 years later. So he got me a backhoe, and we dug up all the seedlings. And this is what they look like after 25 years. So they just keep sprouting. But this is what I refer to as the lignotuber. The fungus will kill the stem, but it doesn't kill the lignotuber. It doesn't get in there. And so it's able to generate new stems. And on top of that, it also generates a new root system. So that's what distinguishes a lignotuber from just a stump sprout, is it's got the ability to generate new roots. And it's a very different kind of twisted grain that makes it very hard for fungi to get in there and actually kill it. So this is the nature of the sprouting in the American chestnut. Now, you do see sprouting as a response to fire, but the only place really where fire is a major ecological factor is on the Cape, where you have dry soils. And this is a white oak, and there you can see that after this was a low fire that didn't kill the trees, but it sprouted on the left-hand side. But on the right-hand side, that was a better major fire that actually killed the main stem, and you get those sprouts from the base on the white oak. And if you go to California, I'm from California originally, you can see here, this is tree species that do well in fire are much more common. This is the California bay laurel, Umbellularia californica, and you can see there are 3 generations here. There was the original stem that then got killed, and then the second generation was black that died in the most recent fire. This was about in Santa Rosa, California, about 8 years ago, and then that's the 3rd generation of stems, all responding to the sequence of fires. And the reason it's such a fabulous sprouter, you usually don't see the lignotuber in the bay laurel, but this was exposed by erosion, and this is the origin of those sprouts. So this is that special rejuvenation tissue that allows, and this bay laurel will continue sprouting even as an old tree. So as I said, a lot of trees lose the ability to sprout when they're young, but the certain species will keep it well into the later life. Now around here, some of you may be familiar with the linden trees, and when I worked on the hotline here at the Arnold Arboretum, if you can imagine that we had a hotline and we take questions from the general public. The question was, I want to get rid of those sprouts along the base of my linden tree. Is there anything I can do about it? And the answer is no. Between a rock and a hard place, you can see it sprouts. And the reason you can't get rid of it, on the right-hand side, you can see the lignotuber, because of the compacted soil, as opposed to being underground, it just rose up to the surface. And they're going to continue sprouting for as long as they live. And so tilia this is, as I said, this is the best example of what I mean by the insurance policy. It invests a huge amount of resources into developing that lignotuber that then allows it to survive. And in their native habitat, they grow on steep slopes, and so you have chances of disturbance happening are much greater than if it was on a lowland environment. And this is what the normal form that a tilia takes. This is along the Housatonic River in Cambridge, where very close to the edge, where big chunks of ice are always coming down the river and washing against the tree, and it just keeps sprouting repeatedly. So the idea that all trees just have one stem, well, no, that's not necessarily the case, depending on the habitat in which it grows. So this is the normal form of the American linden. Now, as many of you know, I've done a lot of work on ginkgo biloba, and ginkgo biloba is a mountain species in China. There it is on a steep slope on Tianmu Mountain on the left-hand side, and then on the right is the old dragon getting ready to fly, one of the more famous ginkgos. And you can see that the one species here, this is the original stem right here. The wall wasn't here when it sprouted. That got built later. Then this is the 2nd generation. The 3rd generation, and when I was there in 2007, there was a 4th and a 5th generation. So it just keeps moving back, trying to achieve a higher and higher degree of stability over time. And the thing that was, when I was in China in 1989 doing my PhD research, I was surprised to see that China were multi-stem, because all of the ones that are in cultivation were single-stemmed. So it became a question, what's the origin of these multiple stems? And you can see on the left-hand side, when the trunk comes in contact with an immovable object, you get what's called adaptive growth. But in the case of ginkgo, they form what are known as chichis that they grow out over this. And then when they touch the ground, they root and they send up new shoots. So those are not roots. Those are actually rhizomes that they have the ability to produce new roots, but they also have the ability to produce a new shoot once they take root in the soil. So this was pretty amazing to see this in action, but I didn't see it in trees cultivated in North America. I had to go to China to actually see how the tree behaves in the wild. And when you go to Japan, a lot of the trees also produce these, I didn't mean to do that, will produce these chichis, but from the aerial chichis from the trunk of the tree rather than from the base of the tree. And this is something that's phenomenon. And one of the reasons for this is really interesting, why the trees in Japan seem to have more chichis than the ginkgo trees in China do, is that the Japanese, when they brought the ginkgo to China, particularly for religious purposes, they would cut a chichi off, and if you turn it upside down, you reverse its polarity, that allows the shoots to rise up, and then you can propagate it by bringing these chichis in. And so a lot of the ancient ginkgos in China were propagated by people who brought, quote unquote, a walking stick with them. And they planted their walking stick, and it grew into the ginkgo. And so when you propagate a tree from a chichi, it tends to produce chichis much earlier than if you raise a tree from seedlings. So this is a form of bonsai that's very common. You see this in Japan. But it really tells you some idea about what's, this ability to rejuvenate yourself. And I should say, as a little footnote, when I was doing my research, I didn't have permission to collect tissues, any cuttings or anything from the trees in China, but they did give me permission to collect wood samples. So they didn't know that, so I collected little small chichis from some of the oldest trees in China, and then getting them through customs was difficult. But I said, it's just wood samples, But I could carry these around with me for a month without any problem whatsoever. And then I brought them back to the Arboretum and then planted them upside down. And then they produced new shoots. And then I cut those new shoots. I produced new plants from those new shoots. So that was kind of amazing that I was able to do that. And this is the oldest, biggest ginkgo in China. And you can see how the center is gone, but it only exists now as a result of the secondary sprouting from that basal lignotuber. It's just an amazing tree that is, can't prove it, but thought to be about 4,000 years old. And one of the things that I've learned recently, and I'm working on this, is when I was in the Netherlands and Belgium, I went around looking at the oldest ginkgo trees that are in cultivation outside of Europe, and you can see how these trees were under an enormous amount of stress. And you can see these chichis. This is a whole other layer of tissue that's forming along the outside of the trunk of the tree that's going downward. And then once it reaches the ground, it forms a whole new root system, because both of these trees were sort of buried, and then they put soil on top of them, and that stressed them, so they can form a whole new root system from this tissue that once it reaches the ground, and then if things go right, they'll produce new shoots as well. So the ability of ginkgo to survive traumatic disturbance is legendary. Let me put it that way. And as an example, I've worked as a consultant for this ginkgo plantation in South Carolina, where they have 1,000 acres, 10 million ginkgo trees, started in 1982. And I started working as a consultant for them in 1990. And they harvest the leaves using a modified cotton picker in July and August while they're green. They don't want the yellow leaves. They only want the green ones. I have the highest concentration of the active chemical ingredients. And then after they've harvested the leaves, you may think that's smoke coming out of that tractor, but no. It's a chipper. They're running over it with a chipper. They cut them to the ground every 5 years, and that's why they can do it. And this is what it looks like after they've harvested them, because they have to be able to harvest them using a machine. They can't, so they have to keep them lower than 2 meters. And so then this is what happens the next season. It's quite amazing to see how they look. And this is what you find in seedlings, actually. Will produce these lignotubers, these chichis, and they're covered, those little bumps on this the one in the middle, those are all potential buds, and it'll sprout. So even, an old tree, so the trees are 40 years old now or more, but they've turned these seedlings into ancient trees. In other words, young seedlings can behave like 1,000-year-old trees if you keep cutting them to the ground every 4 or 5 years. It's really remarkable that the tree has this capacity to do this. And one of the things that happens when you cut the trees to the ground, they produce, the leaves are, it's a juvenile. This is rejuvenation. And when I use that term, it's reset the clock, not back to where the seedling is, but back to what the juvenile state is. So you get these big leaves on juvenile trees in a lot of species. And then the other thing that's quite interesting is that the blue line is low cutbacks and the red line are higher cutbacks. So they cut them down to the ground and then 10 centimeters up, then 10 centimeters up, then 10 centimeters up, and then they cut them back to the ground again. And so the chemistry of the leaves changes depending on, and the ones that are cut down to the ground have a very different, have much more active ingredients. The active compounds are produced by the root system and then translocated into the shoot. So that's the basis of this variation. And so when they're cut to the ground, and so they like cutting them to the ground because they get higher concentrations of these active chemical ingredients. And of course, the most famous thing about ginkgos that survived the atomic bombing of Hiroshima, there are 6 ginkgos that were within 1 or 2 kilometers of ground zero. They got completely blown away by the thing, but then it sprouted back following the atomic blast. So there are very few trees that can do this. Yes?
Yeah, sorry, Peter. The leaf harvesting, is that for supplement?
Yes.
Okay.
We'll talk about it. I work with the plant. We won't talk about whether the supplement works or not. Okay. So this is the life cycle of ginkgo biloba. You can see here, the seedling phase, the juvenile phase, and then disturbance, which can act at all stages, causes the sprouting and then rejuvenation. So it's this ability to reset the aging clock is quite remarkable. They can't go all the way back to the seedling stage, but they can definitely get back to the juvenile stage. Now, the other species that I've worked on that's very similar, I grew up in California, is the coast redwood. So I took this picture a long time ago following a logging operation in California. And you see all that sprouting. It's like, wow, there aren't many conifers that will do this. And there it is. You can see here, when you cut the stem down, you get these amazing sprouts like that. And you always see in the old growth forests, you see many plants that, multiple stems. And those are sprouts from cutting that happened in the mid-1800s, basically. And this is the largest lignotuber ever described. This is California. There's 8 different huge stems. This is what's underneath one of those clones of redwood stems. It's just remarkable how we call it a burl if you want, but it's really a lignotuber, and the ability to resprout, this is where it comes from. And this is when you go into redwood forests, this is what they look like, the burls on the side. And they used to cut those off and then sell them to tourists, and you could take it home and put them in a dish of water, and they would sprout up. In fact, the first tissue culture ever successfully done with a woody plant was done with the sequoia using the sprouts from, that was the source of the tissue culture with redwood. So redwood was the first tree that was successfully tissue cultured using these sprouts from the lignotuber. And then that one on the right just reminded me of what I saw in ginkgo biloba. You don't see those very often. But what's interesting is that, like in ginkgo, in redwoods, they start when they're seedlings. So on the left-hand side is a 4-month-old seedling, and you can see this sprout. The origin is the node, the cotyledon, those are the cotyledons, and the sprouts that come in the node of the cotyledons, that's the origin of the lignotuber. So it comes from a bud. It doesn't come from, the root tissue or stem tissue. It comes from the bud tissue, and you can see here, that it's really beginning the process of developing into a lignotuber. So that's one of the key elements of the lignotuber. It starts in the seedling stage. You can see this, and that's quite remarkable. And then Faye gave me this picture of an olive tree. This is the third of the great triumvirate, as I like to talk about. The redwood, the ginkgo, and the olive are the 3 trees that all produce the same type of tissue. And this is a 1,000 or 2,000 year old tree, and you can see how it's beginning, just looks like that old ginkgo that I showed you in China. And just like the others, it starts as a seedling. This is where the lignotubers are forming that's the cotyledonary node right there. And this is a tree in Tuscany that's forming chichis, just like you saw in the ginkgo. And then it's got this ability to sprout like crazy. And so this is what I call this triumvirate of trees are all capable of what I call ecological immortality. It's not real immortality because, as you know or may know, that the olive trees are undergoing, there's a huge disease that's wiping out the old olive trees throughout Europe. So there's nothing the tree can do about that. But in terms of dealing with other types of ecological conditions, the tree's got an amazing ability to withstand them. So I call that ecological immortality. So those are the great triumvirate of trees. The ginkgo from Asia, the redwood from North America, and the olive from Africa and the Mediterranean. So it's really amazing. Now, looking to another type of rejuvenation would be the root suckering. So this is sweet gum. This is a famous article, and you can see here, these are meter square plots, and you can see how the proximal end of the root has not expanded at all from when the sucker formed, but the distal end is formed. So, are these root suckers returning any of their resources that they're producing to the mother trunk? The answer is no. It's keeping them all for itself. And you can tell because the diameter of that part of the root has not expanded at all. So you call, the whole thing is a clone, and that's known as a genet, but each individual stem, if you're counting trees, is a rammet. So that's how you distinguish it. So when you're, and a lot of people who are counting trees in forests don't recognize the fact that you're looking at sprouts. There aren't distinct individuals. They're just individual stems. So that's something that, people have to be aware of when you're doing census work in the forest. Now, the biggest clone is Pando, quaking aspen. Estimated to be 14,000 years old, which is when the glaciers retreated from the Intermountain West, the Great Basin area, 47,000 stems, and a mass of 6 million kilograms, and all sprouting since the glaciers retreated. Now, this clone is starting to decline a little bit. It's getting smaller, and people are worried about it, but you'd think after 14,000 years, maybe there is a limit to how long you can live. And this is another populous species, Angustifolia, in Wyoming, growing along the side of the river. And here you can see how the ability to root sucker really is a very good adaptation, because this is very unstable soil, and being able to reproduce from root suckers is really going to allow species to remain there no matter what happens to them. And in our own forest, Sassafras albitum is one of the most common of our root suckering species. In fact, this was the first crop that was sent from North America to Europe for its roots because it was used for medicinal purposes, and you could cut it down and it would come right back. So it was a sustainable product. And so one of the reasons there's it's such a common species here is that it was widely harvested and sent to Europe, which just tended to propagate the whole species across its entire range. Now, when I worked at the Harvard Forest, I wanted to show you this based on research I was involved with. I was working with Comptonia peregrina, studying a nitrogen-fixing plant, and we had to grow the plant. And Dr. Torrey, who was a plant physiologist, he was very interested in the process of root suckering. Why is it some species can produce shoots from the roots, but not others? And so he would grow the roots, isolate the roots, cut them off from the plant, and then grow them in liquid culture on a shaker. But they weren't producing any shoots when they do that. And he discovered that when you added this compound, a sugar alcohol called myoinositol, all of a sudden they would start producing shoots. So in other words, myoinositol was the compound that the stem, when they send the carbohydrates down to the roots, they don't send it as the carbohydrates we're familiar with, they send it down as myoinositol. And that's what the roots are used to. And this is what, and what's really interesting is sugar alcohols are having a moment now. People are very interested in using them for medicinal purposes. And myoinositol is now something they talk about for human medicinal products. So this is something people are just beginning to understand, that these sugar alcohols are not just alternate forms of carbohydrates. They actually produce very different physiological impacts on the plants and on people as well. So this is something that I think is going to become really interesting in the future. And there you can see that's the piece of root that we induced using the myoinositol to produce those new shoots. Now, I'm a big fan of the ailanthus tree, although everybody hates it. But you don't see, this is in York, Pennsylvania, probably the most magnificent ailanthus I've ever seen. And if you don't cut them down, you leave them be, they're actually quite beautiful. And this is at BU, Boston University. This was a magnificent tree in front of one of the buildings. Which building was it in front of? What? The communications building, yes. Right next to WBUR, right? They cut it down, 10 years ago or something like that, unfortunately. But if you leave it alone, you don't get these root suckering. But this is what you talk about ailanthus. Most people think about it, and they think those are seedlings. But the root, wherever you have the blacktop coming against the wall, you've got a seam there, and it expands and contracts. That's where water collects. That's where nutrients collect. So that's actually a great place to send your root. And then they cut the main stem down, and then that releases all of those root suckers. So it's really kind of interesting. And this is what, I took, a friend, one of my former students took this picture for me in Boston Harbor. This fell off the cliff here, but you can see the entire clone of the ailanthus tree in that spot. And it's really remarkable. And I just put this slide in just for this talk. I love this quote from A.J. Downing. We may as well, and he was add, for the benefit of the novice, the advice to shun all trees that are universally propagated by suckers. It is a worse inheritance for a tree than drunkenness for a child, and more difficult to eradicate. Even ailanthuses and poplars from seed have tolerably respectable habits as regards radical things. So he hated the ailanthus tree. He was fond of it for the first 20 years. It was introduced as it was the first most common street tree in New York City beginning in the 1920s, got planted everywhere. And by the 1950s, people really started to not like it so much, and they tried to get rid of it by cutting it down, and that just increased it. And it's been sprouting. Nobody has planted an ailanthus tree in New York City for at least 100 years. And it still is the most common tree in New York City. And if you look at the inventories of street trees in New York, they don't even count the ailanthus because nobody planted it. Yet it is the most common tree in New York City. But I like this idea that if you propagate a tree from a root sucker, that is going to produce more root suckers than if you grow it from a seed. Now, I don't know, I haven't proved that scientifically, but there's quite a bit of evidence to suggest that that might be the case. But I haven't done that work yet. But I love that quote, comparing sprouting to drunkenness. Now, another species that's famous for its ability to sprout is Robinia, pseudoacacia on the top. These are in northwest Connecticut. That's a stand of trees that were uncut. They were planted and uncut, and on the bottom, adjacent to it, is a similar stand that was cut. And you can see that amazing ability to resprout. And that's why, this is on the left-hand side is the original range of Robinia. It didn't quite make it into New England. It was made it to, central Pennsylvania, which is about as far as the glaciers came down. It was headed towards New England, might have gotten here in 500 years or something like that. But this is its actual range now because the wood is incredibly rot resistant, And if you cut it down, it sprouts, so you can use it. It's sustainable, and so it was the perfect wood for making fence posts. So farmers planted this as a source of sustainable production of wood, and not only in North America is planted, it's all over Europe, and it's all over Asia as well. Everybody, I call this America's gift to the world. But the wood is now experiencing a comeback because it's fungal resistant, so it's organic pressure treated. So when they build playgrounds now, and they don't want to use pressure treated lumber, they use black locust. And so black locust is now worth a lot of money if you can find it in the size that you want. So it's experiencing a comeback. So, this whole idea of going back to the original, it should be considered invasive in Massachusetts, that really annoys me. I spent, months trying to fight that because I was on the invasive species committee for the state. And I did hold it off for about 6 months, but finally they kept calling for votes, and then they brought in people on the phone, and I lost the last one because they brought like a half a dozen people on to vote who weren't even in the room. But, this is just the way it is. And it's actually a useful plant. And all of the timbers, and you can see in its range in the Appalachians, for the coal mining in Appalachia, they were all supported by black locust because it's so strong. So timbers for mining and for fence posts are the two main things that it was used for. And, another root suckering species is American beech. And, the beech leaf disease is, a lot of the original beeches died from the stem disease, and then the root suckers came up, and now they're getting whacked by the leaf disease, which is really sad story. We don't know how it's going to end. But the European beech, Fagus sylvatica, is distinct from the American beech because it doesn't produce any root suckers. And so if you're worried, trying to figure out is this an American beech or a European beech, just see if there's any root suckers. And so that's a trait associated with a root system that distinguishes these two species. But the European beech is really effective at reproducing from layering. These are, and you can see the proximal side of the root the stem hasn't expanded at all, but once it takes roots, then and it changes reorients itself, then it keeps all of its resources for itself. It doesn't send any back to its mother. So it's not a very dutiful daughter, if you want to call it that. And this is over here in Brookline, the famous beech grove planted 175 years ago. The original trees are not doing so well, but they've all layered. And it's just an amazing place to go. And you always see this shape. That's how you can tell it's a layered branch. And Norway spruce, quite a few conifers. This is vegetative regeneration in a lot of conifers. Particularly old specimens where they have full sun and they keep their lower branches, and then as they get older, the branches get heavier, they touch the ground, and then they take root. And then once they take root, then they reorient themselves. And this is, when you go to these old estates, you often find, like the Honeywell estate, lots of plants that look like this. And remarkably, the oldest tree that's been documented on the planet is a Norway spruce growing at high elevations in Sweden. And you would hard be pressed to know that this tree is almost 10,000 years old. But they did it by finding wood underneath here and doing, carbon dating on that, and it is 10,000 years old. And the tree has been layering repeatedly for 10,000 years, even though no stem is, only maybe 20 years old. So it's really remarkable. This ability to layering really promotes the longevity under stressful growing conditions. And you see this, in any tree line in a lot of conifer species like this Picea engelmannii. And I've done a lot of work on hemlock, Tsuga canadensis. It's a massive tree, beautiful tree, and the adelgid has really damaged it. It hasn't wiped it out, but it has damaged it. And I think that I've noticed the mortality associated with adelgid seems to be going down. They're not killing them. Used to be after 5 or 10 years the tree would be dead. Now the trees are lasting much longer. So I don't know what's going to happen to it. But one of the things that on Mount Wachusett that Dave Orwig and I did, we discovered that there was an ancient hemlock forest there. We discovered that hemlocks will layer under the right conditions. And this is the only time I've ever seen this, and has never been reported except in cultivated specimens in gardens. But you actually can get layering in hemlocks in the wild. And this is what it looks like. And you can see here the mother stem here, right there, 200 years old, and then those are the ages of all of the stems surrounding it. So it really is, this is where longevity comes from. And then this is layering is a two-stage process. The auxins produced by the apical meristems accumulate at the end of the branch at the base of the stems in contact with damp soil. This induces the branch to form adventitious roots, which then produce cytokinins that promote the physiological rejuvenation, i.e. the reorientation of the branch distal to their point of attachment. So you know when the branch upturns like that it's taken root. If it doesn't take root, so pitch pine is a species here, you're familiar with that grows on the Cape. You see a lot of branches way down on the ground, but none of them ever go up. They all remain horizontal, and that's because they don't layer. They don't form adventitious roots. If they formed adventitious roots, you'd see those branches going up. And so that ability to form a new root system rejuvenates the stem. And that's one of the principles I'm going to talk more about, but that's a really important part of this. Now, people have figured out how to utilize this ability of trees to resprout for their own purposes through pruning, and you can see the illustration on the left, Oliver Rackham, just shows you how the before cutting, after cutting, and then 1 year later. And so coppicing and pollarding are taking advantage of this ability. And the Europeans picked certain trees that they knew would respond like this. And the whole point of this was to produce small diameter wood that could be used for cooking. Because when you're cooking on a wood stove, you want intense heat for a short period of time. You don't want to throw in a big log because it takes forever to catch on fire, but a small diameter wood will catch on fire right away and give you a lot of heat right away, which is all you really want. So that was the purpose of all of these pruning strategies, was to produce small diameter wood. And it could also be used for making fences and basketry and stuff like that. And in China, you still see people out, and you go out in the outback, harvesting, as in this wood for very small diameter wood, and then you go back into the woods where they came from. This is what you see. The trees that have been cut like this, coppiced for decades, if not centuries. And it promotes this longevity. So the pruning, this is one of the things people don't realize, that the pruning really, over time, promotes longevity. So this is 600-year-old little leaf lindens at the Western Bird Arboretum. They've been pruning it for 600 years, which is much longer than Atilia cordata usually lives. So the pruning promotes longevity because it stimulates the production of a new root system. And once you produce a new root system, that allows you to start your life over again. So coppicing essentially turns trees into shrubs. So this is the Tilia cordata. And you get multiple stems, and then where they touch the ground, they form a new root system. So that's really what this is all about. Now, shrubs, of course, a tree is an organism, a single-stemmed organism, if it's not just damaged. If it's damaged, it's multiple-stemmed, whereas a shrub is multiple-stemmed in the absence of any damage. So that's really the way I distinguish a tree from a shrub. And this is, the tree is, 150 years old, the shrub here, but no stem is more than about 20 years old. And this is, you see how it's the clonal growth in this staghorn sumac, or this gray dogwood spreading by rhizomes. And then from the Arnold Arboretum, this gray dogwood was planted in 1873 in the area between the roadway and the walkway. And every 5 or 6 years, we cut it down to the ground, and it's been a hedge. This is right between the two ponds there. And it's amazing that we've been pruning it since 1873. So this is one of the it doesn't seem very intuitive that cutting the plants back would increase their longevity, but there's lots of evidence to show that that is exactly what happens. And then because I work at this is the Arnold Arboretum, and I worked here for so long, I can take pictures of the same plant over time. And so this is a pawpaw over on Peters Hill. We planted it in 2003. It was 24 years old on the left-hand side. And there it is, 30 years old, starting to produce root suckers. And at 30 years old, here it is this year. That original stem is long gone, and it's formed this amazing stand. So I don't recommend planting pawpaws if you have a small garden. But if you've got a lot of land, you can do it. And it's just amazing to see how this aging process happens over time. Now, bringing it up into today's world, the ability of trees to resprout following disturbance pre-adapts them to deal with environmental unpredictability caused by climate change. And this is those 150 years of hurricanes on the East Coast. And I did some research in Rhode Island, in coastal Rhode Island, after following Hurricane Sandy, which dumped over a foot of sand. It pushed the sand up there. And if a lot of trees and shrubs were not able to withstand that, even though they can sprout pretty well, but having a foot of sand dumped on you was too much for them. But it was not too much for Rosa rugosa. And it came back, so that's bayberry in the background there, closer to the ocean, and that was not able to survive that deposition of sand. And what's really interesting is back in the 2000, when I on the Invasive Species Committee, and we were deciding what to put on the list, somebody came from the Department of Environment and said, whatever you do, please don't put Rosa rugosa on the invasive species list, because we need that plant, because of its ability to withstand this type of disturbance is so great that it offsets any potential damage that it might do as an invasive species. So we dutifully did not put it on but I can't guarantee you that is going to hold. There may be some extremists out there who insist on putting it on the list, but this is an amazing plant, and this is what it looks like after a storm has come through, and it resprouts from stems, from layers, from rhizomes. Its ability to tolerate just shifting sand is really, really important. And these are the plants that are going to be super important in the future. So rather than banishing them, we need to actually, we need more of the plants, plant more plants like this. And I love this picture. I took this picture in Kauai. This is a casuarina from Australia. This is where it was planted on top of the dune here. This is the original root system. Erosion took place. It developed a secondary root system here. More erosion, third layer. More erosion, a fourth layer. A fifth layer, a sixth layer. So this ability to produce new roots in the face of damage is just really, really important for plants that have to deal with unstable environmental conditions. And just to getting close to the end here, this is about the root systems, the ability of trees to generate new roots. You can see that's wound wood that grows together, and when that wound tissue, if it's rotten on the inside, it keeps growing, and then when it's dark and it's moist in there, then it produces a whole new set of roots on the inside, endocormic roots. Jim Popinger, I think you showed me this oak tree when I took a picture of that about 40 years ago. And these are some endocormic roots on a red oak tree. They're actually supporting this old tree. And then that's a gray birch growing along the Charles River in Cambridge. And so this this ability to start over again by generating a new root system is really critical to this whole concept of rejuvenation. And I think I learned this by taking care of the bonsai collection for 35 years that I did here at the Arboretum. And, you know, every 4 or 5 years, you take the plant out of the pot, and this is what you find in it. And it's kind of, and you cut all those away. You remove at least 30%, if not 50% of the root system, because those roots that are girdling, they'll never straighten out. And so you cut them all off, and you rejuvenate the root system, and you put it back in the same pot. So here you can see this is a Acer burgerianum, the trident maple. This is the way it arrived from Japan in 1913. This is the way it looked in 1933, and here it is in 2000, in the same pot. So you don't want to keep putting bonsai into bigger pots because then you could never move them. But by keeping it in the same pot, and so it's that cutting the root system off. That's what's important. It's not the pruning of the top that's important. It's the pruning of the roots that are important. If you don't prune the roots, the tree will die within 10 years. So that's what really bonsai is all about. So this is my last slide. The ability to generate a new root system following disturbance is the secret of rejuvenation and resilience. Some species are better at this than others, and this pre-adapts them to be able to deal with stressful habitats and climate change. As such, these plants have an important lesson to teach us about the future. Adapt or die. So on that note, thank you very much. So the pizza's still warm, right?
Pizza's still ready to go now, and we can have our talks there, or we can have a.
I was going to say, we have such a nice group here. Do we want to just go upstairs and have some conversations, or do you want to take a few questions?
I can take a few questions.
Okay,
Take
few questions and then pizza.
I have two questions, Peter. One an evolutionary one and another a morphological one. Evolutionary being, well, you definitely convinced us that it is a great idea to resprout, right?
Right.
But is that something that plants have been doing from the very beginning? They
well.
inherited that from their ancestor, or is it something that is continuously evolving?
Well, as I like to say, ginkgo invented it. No, and conifers, gymnosperms in general, do not, have very limited ability to resprout. So those species that figured out how to resprout, so that increases the lifespan of the individual. And when you increase the lifespan of the individual, your chances of successfully reproducing from seed are much greater. So that's the evolutionary impacts of it, is it increases the likelihood that you will actually reproduce from seed successfully. But it took a while. Now, herbaceous plants are much better at sprouting. They have to than woody plants. So I've focused only on woody plants. So it's going back to the deep evolution of plants, that I can't really answer your question. I only really deal with woody plants here.
Right. And the morphological one, when you were mentioning about the origin of chichis, that you said that they come from a bud, like what does that mean? Like it actually has a meristem?
Well, there's a meristem. It has to have a meristem. They can't. This is one of the things that German morphologists have, argued about for, centuries. It seems to be able to create a bud on a stem. You need to have a bud. It's hard to do it from nothing. In other words, an adventitious root just comes from the meristematic tissue, but generating a bud is much more problematic. And usually, they don't just come from meristematic tissue, they come from pre-existing buds. I don't know if you want to add something to that, but
No, but I was going to say, just thinking back to the Carboniferous, and you think of the arborescent horsetails, I mean, those would all have also been rhizomatous.
Absolutely.
And so, this strategy has been around for a while.
Yes,
and,
absolutely.
In terms of trees, it's just that some of the tree groups that did it early on are now extinct. But I am curious a little bit about how many of these cotyledonary nodes have buds versus that can really activate into these kinds of structures.
Well, one thing that looking at gymnosperms only, and I'll only say this, is if you have 2 cotyledons as a seedling, then you have buds, and they tend to be able to resprout. So all the thuyas and that whole family is that. But if you have more than 2 cotyledons, like the Pinaceae in general, they never sprout from the cotyledonary nodes.
Yeah.
So there's something there, but I don't know what it is.
Yeah, you let me the article, is it Buchholz?
Yeah.
Did that survey, yeah, back in the 30s.
It is really, so there's some very complicated evolutionary background on this. Okay, well, should we?
Is there any case, like in making maybe the opposite question, where you think that resprouting would be not a good idea, and that plants actually have evolved very strict developmental programs not to resprout? Like, is that something that happens or not at all?
Well, I think, in my experience, if you can't resprout, the oldest trees, that I've ever seen all have some capacity, and that includes shrubs and, without the capacity to resprout, you're limited. What happens is, like, you think about the bristlecone pines and the White Mountains of California, they get, as the tree gets older, the roots get further and further away, and the process of sending nutrients and water back to the main stem becomes much more complicated and expensive to do that. And so when you can form a new stem, you bring the root system back closer to the stem, and you don't have to do that line. But I'm working now on the bristlecone pine, and I think that they have actually figured out a way to generate a new root system and escape the fact that their old root system is so far away from them. So even something like the bristlecone pine that does not resprout has the ability. The key isn't the sprouting, it's the ability to generate a new root system that really promotes longevity. And they do that through this thing called strip bark, where one part of the stem. But what's interesting about that strip bark is it's not just bark, it's like a whole layer of tissue. It's a special kind of rejuvenation tissue. And it connects to the root, but it causes a regeneration of the root system. That's my theory anyway. I'm going to go next year to excavate some of these old trees and see if we can find something interesting about it.
But Daniel, I'll just say quickly, it would be great to look at phylogenetic context. So let's take the beeches. How do we know that the European beeches haven't lost suckering as opposed to the American beeches having gained?
Well, what's interesting, if you talk to nurserymen, who a lot of times if you dig a bee tree from a nursery and you leave the root system behind, they'll often sprout. But they won't sprout if they're intact. So there's something there, but it just isn't, something has to turn that gene on. So it's not that it doesn't have the gene, but it's just suppressed. And there's quite a few trees that if you talk to nurserymen, they'll tell you when you leave it in the ground, you'll get the sprouts. But if you remove it won't do it if you leave the tree intact.
All right. John?
I think it's it's the evolutionary constraints. Like the Pinaceae, as a group, don't resprout at all. Whereas the Thuyas, they like Metasequoia and the Sequoia. Well, Sequoia will resprout. Sequoia dendron won't resprout. So it really, I can't answer that question because it really goes back to you have to understand the deep evolutionary history.
Well, all right. We'll stop here because but come up, have some pizza. We're not done with you guys. And again, thank you, Peter.
Oh, you're welcome.